We're going to continue the lecture 9. I decided that there was enough, in fact more than enough stuff in lecture 9 that I cut basically the file in half. So there's now a lecture 10, which you're looking at here, that has most of the things that were mentioned on 9, and we really only got to here. So today we're going to go further, but I will review this because these transformations from the crank way of describing a rotation or a Hamiltonian and the Euler angle way of coordinating it is really key to a lot of this group theory, but certainly any group you would want to look for different ways of doing both of the processes we do in physics, and one of them is to keep track of coordinates that are not subject to the vagaries of group commutation, and then on the other hand be able to parameterize rotations in an intelligent way, and usually those are separate jobs as they are here. The Darboux crank vectors with their funny polar angles, and then the Euler one here, which by the way I think you've noticed that I always use parentheses when it's Euler angles, and I use the braces, brackets I guess you would call those, when I'm dealing with the Darboux coordination of rotation. Anyway, that's what we're going to be using today as we discuss, well, first density operations. This will actually make some of the tricks that we've pulled going between Euler and Darboux and between crank vectors and spin vectors more clear. And also it will give you a chance, I don't know if you've had any contact with the density operator description of quantum mechanics. Good time to do it. It's not that hard. And 2 by 2 is a good place to start. If we could do 1 by 1, but that's too trivial. So 2 by 2 is the easiest example of that. And we've already looked a little bit at the ABCs individually. I'm going to go through that really quickly today and get to the combinations that involve the avoided crossings, which are so important in our modern physics now. And finally, I'm going to end up with our last discussion of optical polarization and a little program that lets you see some of the beautiful things that entails. So let's quickly review what we did last time, and that was make a comparison and in fact a set of formulas that related the Euler angle azimuthal alpha, the polar angle beta, and the inside twist angle, the gamma azimuth, as seen by the rotated frame. And the rotated frame is indicated by the sphere there that has its own x, y, and z axes that are being transformed from the laboratory x, y, and z. So I pointed out right away last lecture that the Euler angles that are coordinates for the spin vector, in fact the whole body there, are things that we'll be taking on later on as we discuss the higher representations of the spin that we're working on right now. But already we have a three-dimensional set of vector components that we give the name vector to, that it's become very useful for this problem as well as things that are going to be coming later. So the spin state and its Euler angles are one thing, and the operator that moves spin states with its three parameters, the azimuth of the crank vector, the polar angle of the crank vector, which is just exactly that angle right there. We did a rotation with it about 34 degrees in the last lecture. In any case, there's the polar coordinates, three of them for it, and it's the same here, cosine sine, and then sine sine, and then cosine. The same arrangement of cosines and sines. It's just that the azimuth here is very different interpretation than the azimuth of the spin vector as far as the group theory that we're doing goes. So what we did was we made a transformation between these two in the situation where we wanted this operator to be exactly the same operation as this one. And that was done by taking the operator matrix apart into its four spinor operator components, both for the Euler representation that dealt with the coordination of a spin up, spin down quantum angular momentum half, and the rotation operator that would produce this in general with a single crank rotation, also being broken down into four pieces. The four pieces being the Pauli Hamilton, I should say Hamilton-Pauli matrices of Hamilton's quaternions or Pauli spinors. So today we're going to break the density operator for a quantum mechanical system into four of those same four pieces. And we'll sort of bring this whole description here together by doing that. So, and please ask any questions you might have about this particular thing, as well as the conversion between the two, which were these formulas that related alpha, beta, gamma to the italic phi, the italic theta, and the uppercase theta, which is the total rotation angle. Now today, this theta will be broken down as the uppercase omega times time. This is a rotation angle. Hamiltonians, which we will be working with, have as their units frequency. If you've taken the h bar off, you were talking frequency. So our uppercase theta will be equal to uppercase omega, the horseshoe, times time. So we'll be using the horseshoe symbol for the Hamiltonians. And here, when we use a horseshoe, it will mean the rate of the crank turning in time will be the angular velocity omega. Radians per second will actually be the units of this particular variable in our description of dynamics. We've done this already, I mentioned it already, but I want to remind you of that. Then there was this, where we actually had the thing rotating first 2 pi, 360 degrees. That's the returning to the same orientation relative to the laboratory as it started in, but the Euler angles were not back yet. Here's a dial on this side where it was on the other side before. And I should mention, and I didn't mention this last time, if you grab a hold of this ball and hold it at the 0, 0 position, you can swing the frame anywhere. I'll go ahead and do that right now just to show you what I mean. If I get this crank out of the way here, I can grab the ball in the 0, 0 position, and without moving it, you see the other coordinates, alpha and gamma, can play alpha minus gamma equal a constant, and the ball will not rotate at all if I were to, hold it in the right position. Okay, so when you actually want to rotate this thing with this operator, and you just set it up in sort of an arbitrary position like that, okay, and that's what we're going to be talking about when we talk about eigenvectors of a Hamiltonian, and that's one of the topics today, is to show that. But if I put this thing there and then set it up very close to the North Pole, and then rotate this thing, and then I'll have to help it because it's not sticking very well there. Actually, I can probably make it better by a little spit and polish.
It may have shifted.
I need to get it a little bit wet here.
It may have shifted from your base position.
Which one?
It may have shifted from your base position.
Oh, I don't care about that. I'm just doing a random rotation here just to show you a little bit about how this works. All that's happening when I do this rotation is I get a little bit of oscillation in the beta, but you see there's none of that fancy business. When I come around with 2 pi, everything is back where it started. The carriage is going about as fast as I'm rotating here, you see. So that is the usual thing. It's only when you go to that what's called gimbal lock in the terminology of gyroscope manufacturers, gyro compass manufacturers. This is what's called gimbal lock, where the carriage is supporting a gyroscope, okay, gets locked in this position, you see, and this thing spins around, you see. That was resulted in the death of a lot of pilots who are doing acrobatics in the early days of aviation. If you did a lot of acrobatics, you could get your gyro positioner gimbal locked, and then its reading would be useless, and if you're using your instruments to maneuver, you're dead, because your brain is not very good at keeping track of orientations and Euler angles at high speeds. Okay, but what I wanted to show you is if you're close to the pole here with the rotator, which is thing, then basically it's just going to follow you around. It's only when you get to this point and then you grab a hold of it, you see, so that you can rotate it, and it does this thing will go half as fast. There are 2 extremes. I'm closer to the this crank is closer to the laboratory zenith than it is to the body zenith. Okay, and I'll just set this thing up out here so that I have no possibility of getting gimbal lock, and I will rotate if I can. I wish it wouldn't. Let's see if I can get this to work. There is a typical rotation where it will go to that point and then turn around, you see, and come back. And that's probably, I should have set the thing so that the bearings down here are not so tight. And also this thing not so slippery. In any case, let's just set it up this way, and what I'll do is I'll put it here. I think I can put it way down here at the bottom. I'll get it done about like that, and I'll see if I can get that. Yeah, that's probably where I want to be, about there. That's as low as I can go. Pull this trick I'm going to try to pull here. Let's see if I can make it happen. I'm trying to pull it the way it's supposed to go. It'll go to there, and then, oh darn, it's almost, it's doing what it was doing yesterday, and that is, I've got to get some new suction cups that will stick on the thing. let me bring it up first of all to say about here where I think we can show this. I keep hitting that the the cut to this thing when I'm doing this. I'm trying to avoid that. So let me first do this. I'm just going to go down here and get close to the pole, but this is sort of cheating. But you'll see it if I don't slip. Okay, here we go. All that's going to happen is the alpha carriage is going to oscillate. It will not go all the way around, you see? So this is a case where the alpha carriage oscillates, beta there oscillates, you see? But gamma continuously goes through 2 pi, okay? And it goes through 2 pi once for each rotation of the crank. Okay? So this is a case where my angle between the crank and the zenith is larger than the angle between the crank and the body zenith, which is only about 10 degrees or 20 degrees there. Okay, now if I do the opposite of this, and that means take this completely apart, and now the suction cups are sticking finally, and go up here with a small angle with respect to the laboratory zenith, but a large angle with respect to the body zenith, okay? It's when those are equal that we get the cut that I keep hitting. Okay, so let's try that. Now, what's going to happen, if it will respond for me, and that's because I've tightened this one too much, that it's not behaving well. I'll just show that the alpha goes around 2 pi for every 2 pi this goes around. But the gamma now just oscillates, you see. There's a little bit of an oscillation there, and you can see it probably a little better if I just drop it down right about there. You can see that the gamma dial, boy, that's really slippery. It's as though I put grease on this thing. It's just not holding. We need to use plastic or something like that. But here we go. I think it'll do it now. You can see that it's slipping, but basically what's happening is the alpha now is the one that goes around. The gamma just oscillates. You can see it oscillating just a little bit from its whatever setting it started at. But that's a completely different motion. That's one way for the thing to rotate with the crank close to the laboratory and the zenith of the body quite distant. In those cases, you don't see this miracle here. This is very special, where we started at 0, 0, 0. Okay? That's quite special, that we can get this thing to behave like a spinner. Most of the time, it's more classical. All right, and this stuff, of course, is connected to all of that. All right, let's get down to business here. Enough playing around. It's time for Fano's density matrix theory, which is much more elegant than it has become much more elegant by this group theory than what it was when it was first discovered. But in any case, the idea is that we have these Euler phase angle coordinates, alpha, beta, gamma, for a state. And we have a relationship which involves the phasor, x1 for coordinate, p1 for momentum of number 1 oscillator, whatever that is. And the x1 and the p1 are given those cosine-sine relations with the sum of alpha and gamma and the cosine of beta the sum over 2 and the beta over 2. And then the second component here has a coordinate and momentum of x1, x2, and p2 that is related again to a cosine and a sine, but this time the difference between gamma and alpha, and this time a sine of beta over 2. So this is another way, a funny kind of four-dimensional variables, but phase variables, okay, that's quite different from the 4 dimensions that we had for the crank vector. So we're going to be working with our density operator to describe the state, an operator that describes the state all by itself, not an operator that gets you from one state to another. This is going to be the state. So we would like to take into account the expectation values that we've shown before of those 4 quaternion operators, but mainly the 3 Pauli operators, x, y, z, a, b, c, that we've been working. Here's z right here. And if you recall, the expectation value for the unit operator and the sigma z were the simplest ones. This expectation value here is simply the scalar product of the bra of the wave function and the ket of the wave function. And the result was the sum of the squares of the real and imaginary parts, namely the sum of the squares of momentum 1, position 1, momentum 2, and position 2, x and y, if you will, momentum and the coordinates being summed up. So here's our 4-dimensional sphere in this 4-dimensional phase space. If this is constant, as it is for Schrodinger type quantum mechanics, then that's corresponding to a 4-dimensional norm, you see, and the normalization constant that we're going to be putting on that. We're usually going to have this thing sum up to 1 because x1 and p1 are given by sines and cosines and things whose square add up to 1. So if I don't put that on there, this is a wave function of unit norm. But we want a 4th variable so that we can let this thing grow as we will when we use this thing to describe electromagnetic oscillators. But taking this and scaling it by a half gives you this. So this is the normalization over 2. Here's the sum of the squares of the wave functions over 2 with a 1/2, okay? And then 1/2 of this, okay, same thing. So now it's a difference between those two, okay? Now we're looking at cosine squared of beta over 2 minus sine squared over beta over 2, not plus. Plus it adds up to 1, which is what this is doing. So if that's all there was to this, this would be pretty simple. But we've got 2 more things to worry about here. We've got here z, we need x and y. We've got here a, we need b and c. Okay? So here's the x, our thing we call b, okay? And there's the x sigma, or b sigma, bilaterally balanced, isn't it nice? And it gives an expectation value here that is a product of the coordinates x1 and x2 and the momenta x2 summed up, okay? Now scale that by a half and you get what's called the real part of a coherence in the density language that we're going to be using shortly, okay? Anyway, that's what we're actually getting is the real part. We're getting psi 1 star psi 2 plus psi 2 star psi 1 divided by 2. That's the real part of the off-diagonal component of a density matrix. We're going to make a matrix out of the psi 1 and the psi 2 things. And this one comes out to be a product of the cosine of alpha times the cosine of beta over 2 sine of beta over 2. That works out to be a simply a sine of beta. The 1/2 is gone from that. And then the last one here of the 4 is old Mr. C, the complex curly current-carrying chiral animal that is normally called Y. There he is with a minus I there and a plus I there, being expected to give. And this one you recognize right away if I used X and Y notation. It's xpy minus ypx, x1 p2 minus x2 p1. Okay, but with a factor of 2, I'm going to scale by 1/2, get rid of that 2 just like I did here. And that's the imaginary part of this product of the different wave functions, psi1 star psi2. Now minus psi2 star psi1 divided by 2, that is the imaginary part of that off-diagonal matrix, and it gives you something very similar to this, namely sine alpha sine beta, after you put that in full angle form. And there are your polar coordinates of the expectation values. This is your spin vector's polar coordinates. Then it has a 4th dimension because you can change n as part of the game here. Okay, so that is what sets up the density formalism very nicely. The density operator is simply your state vector knuckle-knuckle. It's an outer product of the ket with the bra. It's a ket bra instead of a bra ket. A bra ket is just a scalar product, which would be equal to 1 in most Schrodinger textbooks. It'd be equal to n here. Okay, but the ket bra column row, as I've already talked about in the earlier lectures, looks like that. So that is very definitely a metric. So we use rho, I should say Fano used rho as a density. He's talking about probability density, so it was reasonable to make that assignment. Okay, so how you write it? Can you write it so it looks like a matrix? 1, 1, 1, 2, 2, 1, 2, 2. Yes, you can. But of course, these are just numbers, so you can turn them around. The 2, 1 can be turned around, and so can the 2, 1 be back to 1, 2 if you want to do it that way. You see, this one has a star sitting off to the right. Here it's more like what we're used to. So that is how the bookkeeping for a operator that describes a state. The idea is that it will describe a state in sometimes more convenient fashion than just the wave function. The wave function itself, you see, is complex. This thing has a lot of freedom that this one doesn't have, and sometimes that helps you. This is because we're putting them together like that, any overall phase that psi has is gone. The overall phase will not be tracked by this thing. That's not what Fano was trying to do. He wasn't doing information science. He's doing atomic and molecular physics in noisy, heat, boiling environments where statistical mechanics of probabilities had to be meshed with the probability that come from quantum wave mechanics.
Why don't we have the phase there?
Why we do not have the phase there?
Yeah, you said that we
right.
don't have.
Because whenever I take a ket that has a phase,
yeah.
right, and turn it into a bra, I conjugate that phase, right? So what was e to the I f has a factor e to the minus I f here. Gone.
But we have differences between psi1 and psi2, different phase between two components.
If you were to have a psi with a phi that had a different phase, say f and g.
No, the components. Each component has different.
Oh, that's a different kind of phase. I'm talking about the overall phase. The overall phase. The thing that's described by our angle gamma, it's out of here. It will not survive this. This is something for the laboratory, right? The hell with those body people, right? They can't have their gamma. We're not going to track it, okay? But we are going to track the alpha. Okay, that will be part of our, I mean, there it is. See, there's no gammas here. But alpha and beta have survived. Okay, so that's, you know, a little point that Fano wasn't worrying about. He's not doing it this way. So it's interesting to point that out, that our overall phase is out of here. So here's just a listing of the 4 components of the density operator. Here's the actual matrix. Okay, and it has that nice form that allows it to be expanded in terms of Pauli operators. In other words, the density operator is the 3 components of the spin vector times each of the sigma operators plus a unit operator times a normalization with a 1/2 on it. Okay, so there's what it looks, that's a nice convenient way for us to use it, as you're going to see. So the idea is that the density operator rho has a sigma expansion, and that's what you do with every operator that ever comes up in this 2-dimensional quantum mechanics. First thing you want to do is see what its expansion looks like. You see, you want to try it out in the group basis, you see. See what it does. Okay, so there's the algebraic expression right there. Right? Well, this is very analogous to what we already have done with our Hamiltonian operator, right? That's how this all got started. We took an operator, right, that was Hermitian this time, okay, that we knew was going to be using an exponent to perform time evolution. The e to the minus I ht is the solution to the Schrodinger equation if h is constant. And all of these are now being treated as constants, the a, b, c, and d. Or the omega a, omega b, omega c. So you see now these 2 schemes of rotational or spin objects, namely the state's spin vector and the operators, the Hamiltonian operators, omega vector, the crank vector. This is the crank vector, this is the spin vector dotted with sigma. And then there's this leftover thing that multiplies a unit operator that we'll be keeping track of as well. We're going to do as best we can to track the overall phase, even though we're going to use density matrices. Okay, so that's the layout. That's the bookkeeping of the density operator and its analogy with what we've already been doing with the Hamiltonian itself. Now we got to see how these play with each other. But does this make sense so far? Okay? All right, I would say it's the best introduction to density operators that I can think of. And it involves a really nice analogy. Okay, crank vector versus spin vector. So I'm putting those down here, and we're going to have those as our main equations. The density operator is equal to some normalization with a 1/2, and then the spin, actual spin that describes the state of the spin vector, the expectation values of the spin dotted with sigma. That's the operator part of it. This is just the numbers that multiply those operators, namely these numbers here, here, and here. And there they are, actually expressed in terms of polar coordinates of alpha and gamma. Meanwhile, here's this omega vector, which has polar coordinates too, right? Those are those script phis and thetas, plus the overall turn that the thing is going to be doing, which is the magnitude of the sum of the squares of those omegas there. So the Hamiltonian will be written in terms of spin operators or in terms of sigma operators, depending on whether you have a 1/2 underneath it, or you slide that 1/2 into the sigma and make it into a spin operator. So there are the things written out in terms of the omega 1/2, very obviously here, and we're going to keep the sigmas for reasons that make the algebra simpler. Okay? And I always have this stuff that I should be erasing that's covering the transfer. I think you can read that well enough. That may get rid of it. Actually, it may not, too. Oh yeah, that's good. Okay, so we're in business. Okay, so far so good? All right. Well, this is going to be called the Bloch equation. Felix Bloch was one of the first to really make use of this, as far as I can tell from what I've seen. So we're going to see how these play with each other. So we already know that equation of motion is of the Schrodinger equation of motion of a general psi state. Now this could be an n by n thing, but we're still 2 by 2 here. I h bar time derivative, there's a little dot over there to indicate time derivative of the state, is equal to h times psi. And we're going to dagger that. If we dagger it, of course, we got to put a minus sign here. And we got to turn this guy around. Okay? And we got to turn those two guys around. Now, h is already Hermitian, so I don't have to dagger, but if it weren't, I'd have a dagger on there. Okay? Put these together. The idea is that if I take the partial derivative of the density operator, that is the partial derivative of this knuckle to knuckle ket-bra, I get two terms. One's the derivative of the ket, and the other's the derivative of the bra. Both of which have equations of motion which we put together. So what it's telling us is that the time derivative of the density operator is h operating on this side minus the effect of h operating on the other side. Whoa, that's kind of weird. Well, it's not that weird for quantum mechanics people because they know that as a commutator. Right? So that's the Bloch equation. IH partial respective time of this monster, and it is a monster if you have n dimensions. If n dimensions, you got n squared components to worry about. You're really looking deep into quantum mechanics when you do this. And it takes a bigger computer to run this than it does for the Schrodinger by a huge factor if you have a large n. You see, so pray for large and fast computers if you're going to do this. Right? And we do it. We do it in this building. Density functional theory involves sometimes these things. Yeah, I didn't have to, but it's all. Okay, so IH rho dot is equal to H rho. Well, let's try to find out what that is. Okay, what I'm saying is H rho would be H. It's our Hamiltonian written out in terms of Darboux omegas and their polar coordinates in general. Okay, the parameters for the operator crank vector, and then here comes the rho with its spin state vector, the Euler angles presumably being its polar coordinates, but we're not exposing that right now. And that's H rho, and we're going to subtract from that rho H. Well, they flip, and they do not commute, otherwise it doesn't change. We'll show cases where they do commute, but most of the time they don't. Okay, so I've got to write this whole thing out. I get 4 terms here. Okay, one of them is just a unit. Then there's the crank vector dot sigma, and then there's the spin vector dot sigma. Okay, and the it picks up the omega 0 that's sitting in front of the 1. That's the overall phase. Okay? And then finally there are these two together, sigma dot omega and sigma dot the spin vector. And this has got it flipped around. Now these terms here are pretty much the same. So when I do a commutator, I'm only left with these guys. Okay? So it simplifies. They can't, those guys, across terms can't cancel out. I'm just left with the diagonal ones. One involving omega second after a spin vector, assuming I'm operating something over here. And this one, the sigma, the omega gets to act first and the spin second. Okay? So it's the last terms don't cancel. Except in a very special case where they point in the same direction. And that will come up later. Okay? So what we need to figure these things out is our Pauli identity, Jordan-Pauli identity. But it's Hamilton identity, really. But since these things square up to 1, we have a few less i's to play with. But the idea is that this part's going to cancel. This thing's going to have a dot product. But only the cross products are going to survive because we're subtracting these terms. If I were to add the terms, then I'd only get this. But if I subtract them, I only get this, the antisymmetric part. Okay? So that's what I've got. And I've got to take this identity and make it work for us. Okay? So this one comes out to be omega cross S. This one becomes S cross omega. And this is the minus of that, so we've got get rid of the 2. And we knew we had to get rid of that half because we're going from spinor things to vector things. So this is the form that you will see for the block equation for this two-state system. It's really quite simple. But it exposes everything we've learned so far in a very nice way. I think that's really the most important idea, is if you drop, just leave that thing off of there. It's just a placeholder after all. This is telling us that the time derivative, okay, this has no time derivative. We're not going to change normalization. Later on in relativity, you have to change that one too, but we don't now. So that's out of here. I got a time derivative of this, and this of course is a constant, okay? The time derivative of this dot sigma is equal to, and this thing have come together here to give us a positive omega cross S dot sigma. So just drop the placeholder. It tells you that that spin vector, and we know this already, right? This crank vector rotates the spin vector. That's what it's going to do. This is a gyro precession equation. Partial S with respect to t is simply equal, S dot, is simply equal to omega cross S. Okay? I take my right hand and go omega cross S, okay? Draw it as a perpendicular there, and I see that the S is going to go this way. So basically I just put my thumb on the omega vector, use my right hand, and the S is going to go around that way. Let me turn around here so it shows on the thing. Put my thumb on the omega, right hand, S is going to go that way. And that's all it's going to do. And that's exactly what this machine is set up to show. So, thumb coming out. This is coming out of the screen, right? S is going to ride around a cone. Okay? And that's all the Euler angle machine that I was struggling with a few minutes ago. is doing to the spin vector. But of course the spin vector, you see, is a three-dimensional object. So sure, its spin vector does that, but you saw how the Euler angles that go with that thing play funny tricks. So we still have some thinking to do on this, but that at least gets us in the ballpark. Okay, now I'm going to switch off of this only after I'm sure that there are no further questions. You're looking a little quizzical there.
No, just the direction of the
how you
exchange.
yeah, how you think of a cross product is really what it comes down to. Omega cross S. That's the direction that something's going to move. So omega cross S, okay, omega into S. S happens to be right about there, okay. Omega into S, my thumb is into the and down. So it's got to go this way and then come up on this side. But that just boils down to put your thumb on the omega and there's your rotation.
There's a difference.
That's probably the easiest way to do it. Because crank is the main actor here, right? It's the doer, and this is the victim. The S is the thing that's doing. Now, the thing that's going to happen with relativity, these things are equivalent. So you're going to have them both going around in space. Right now we're thinking of that as being fixed. Okay, now one of the things that comes out of this quick U2 way to find eigensolutions, you say, what do I need that for? A 2x2 matrix, I need it. Not if it's complex. Complex, you've got a bit of arithmetic to do when you do all those projection operators and things, right? And if there's a bunch of exponentials, complex arithmetic is not that pleasant unless you're kind of weird. But this is going to make it as easy as possible. Okay, so I'm going to show you the steps to find an eigensolution of a matrix. Okay, I find first the components of the crank vector, our omega, which you remember omega times t is equal to the angle turn vector of the angle turn to crank. Okay, we're talking about the exponent of the evolution operator, so we use the omega. Okay, we expand that. Okay, just as we just done here. Okay, so that I have an omega here. Okay, the 1/2 goes with the spin angular momentum operator, spin angular momentum operator. Okay, so these are Pauli's with a half, which we would call S for Stokes or spin. And there sits omega, not A minus D over 2, but A minus D, and 2 times B and 2 times C. Okay, in our expansion, the way we have just done it. Okay, so the step 2 is to convert the Cartesian coordinates. This is the main thing we have to worry about. This thing is just overall into polar coordinates. Okay, and once we do that, we really would also like to know about the radius omega, which will be our active part of our eigenvalue. So we're going to have, first of all, a plus d over 2 for this thing, but this thing is going to be the sum of the squares. Sum of the squares of a minus d without the 1/2 and twice b squared, which is 4b squared, 4c squared. Okay? So there's your eigenvalue. It's the overall frequency, we call it dynamical phase, and then plus or minus this that will be different for the two states. That's what's going to be spin up versus spin down, basically. Okay? So there are eigenvalues. All right? Another way to draw it. Okay? Here's my overall phase, and then I put in some interactions or something that split me into plus omega over 2 and minus omega over 2, okay, where this is omega. Big omega. Okay, so that's the rate of turn of the crank. All right? This is eigenvalue omega plus omega minus. Okay? And we very quickly see from the geometry of this that the theta here is arc cosine of this thing divided by the omega we just figured out. And then a little bit more looking, and I can see pretty closely that the phi here is the arc cosine of just the b part over omega times the sine. That's just looking at one coordinate. Okay? That means it's the arc cosine of the omega b divided by the square root of the two active non-diagonal components, bilaterally balanced and curling, together give you those angles. Okay? So that works out something like this. Now, step 3 is just to find the eigenvectors. To find them, replace the Euler angles in your general state definition with the corresponding Darboux angles. Azimuth phi replaces alpha. Polar theta, script theta replaces beta. Beta rhymes with theta, but I'm going to make them equal now. Why am I doing that? Because what I am doing is I'm saying, if I've got a crank over here, where can the spin go so it doesn't move? If I've got a crank here, and let's just put him in threatening position, like that. Say the crank is right there, okay? And well, let's make it right there, okay? Where can I put the spin so that it won't move when I turn the crank attached to that sphere? How about right there? Or near there anyway. Okay, the closer I can get to putting that little pointer right on the z-axis of the body, the closer I can get to a situation where the spin vector, none of the Euler angles alpha and beta, will move. Okay? And that's about as close as I can get right there. And you can see that it's very sensitive. I didn't quite get it on, so you saw a little bit of alpha shift there. But it's pretty good. There it comes back again, you see. It's very non-sinusoidal, so, but it is oscillating. Okay, so this is a case where we're really close to the body zenith, but not quite on. So as I turn this thing, only gamma rotates, right? If I was right on, only gamma would rotate. Yeah, and that's the overall phase which we've been ignoring by the density description. You see, this is not part of our discussion when we're doing this kind of game. So I call this spin plus S. What I mean is spin up crank. Spin up versus the crank direction. There's the crank direction, the spin is up. And obviously the other state is to turn it this down. So we start seeing right away that spin up crank is an eigenstate. This will be an eigenstate of this Hamiltonian. Pretty cool. I don't have to do very much complex arithmetic to get this. I just substitute. Okay? And there's the other one. I simply multiply or increase the polar angle of this spin, okay? I mean, and this is something that this device will not let me do very well, okay? But let me just show it to you so that you can remember it. I'm simply going to take the beta angle and pi it. Okay, now the suction cups aren't going to be very happy to go on this thing. But it's the same idea. Now I'm going to go do my time, right? And once again, the spin vector will not move if it's still a little bit of alpha wiggle, but you know, it's very sensitive to me getting it right on. Okay? Like that. So there's the other eigenstate, orthogonal to this one. And I don't care what phase you have, put any number here, including different change in norm, it's still an eigenvector of this. Right? Changing the overall scale factor of the thing does not affect its eigenness. Okay? Now I want to point out to you that the calculations I did up here are not the most reliable. If you're going to program this thing, program it using a function called a tan 2, where you give it both the x and the y components, the y and the x component right there. Okay? Arc tangent of C over B, unreliable, because you don't know what quadrant it is. This makes sure that you know what quadrant you're in the complex sense. Okay? And the same thing with theta. It's an arc tangent 2 of this hypotenuse, comma, a minus d. So when you write a program, that's the thing you should use. You won't go wrong, provided your a tan 2 is working in whatever system you're involved. There has to be an a tan 2. Calculators have polar to Cartesian converters where you put two numbers in and get two numbers out going either way. They're effectively using an a tan 2. That's what a tan 2 is for. So this is worth knowing for any sort of complex arithmetic that you program. Don't try a simple arc tangent or a simple arc cosine. They don't know what quadrant they're in. Okay, quick thing. I call this Gone in 60 Seconds. After that movie where they had a contest, I guess, to see if they could steal a car in less than 60 seconds, right? Did you ever see that movie?
Nick Cage.
This is Gone in 60 Seconds. Can you I give you a Hamiltonian, I give you 60 seconds to give the eigensolutions, not just eigenvalue, right? Get your A, B, C, and D. Convert to Cartesian polar, but in the process, make sure you got the hypotenuse. There's your eigenvalue that you're going to plus or minus to this. Okay? There's the omega 0, it's 10. Okay? There's the omega, that's 8. That over 2 would be 4. This is 8. That's 10. Okay? That's what I didn't quite plot it exactly right. Then you get the angles. Okay? Once you've got the angles, I mean, you can write this thing immediately this way if you want to be really sure about yourself. Just stick those angles in to your eigenvectors. Okay? So this is the eigenvalue that we were just talking about up here. 10 plus 4 is 14, 10 minus 4 is 6. Here are the actual eigenvectors. By replacing the phi angle that comes up here in the alpha place, and then the beta place gets stuck with the angle theta, which in this case is pi over 3. But remember, it's beta over 2, so it's pi over 6 for both the cosine and the sine. And you can rearrange it in various ways, but that's it. So you know, this is something you're checking some weird calculation the computer's doing. You can check very quickly that you're in the right ballpark. Okay. Now, as I say, we've already gone through the A, B's, and C's by themselves. Here's a Hamiltonian that had just a sigma A, no B and C at all. And of course it had an overall frequency. But that meant we had a spin vector, a density matrix that only had one component, the A component. Okay? With plus or minus signs, but fine. That's the crank that's going to work on this. This was the A-type motion that consisted of uncoupled, but possibly different masses, so they had different frequencies, going about their business as though the other one wasn't there. So you could put an eigenstate there in which only the top one ran, the fat guy, would go slowly back and forth in this potential, which is horizontal ellipse, with the big axis this way, the minor axis this way. Or you could go on the minor axis, which is the fast axis. That would be just a motion of the little guy. We went through this before, right? And I'm not going to, if you're reading this on a movie, you can go back and look at that. This corresponds to rotation around the A direction of our thing. So we would go from, if we started with that polarization there, it would change into circular right here, and then turn back into a polarization that was perpendicular to that one on the other side, you see. So there's the B-type initial conditions. Definitely as far away from being an eigenstate as you can get is the equator of this pole. The eigenstates corresponds to spin either aligned with the A-axis or against it. Those are the two perpendicular polarizations associated with asymmetric diagonal A-type Hamiltonians. Okay, there they are, eigenstates. Put them together and you get this sort of behavior here. This is the picture of the frequency map of the eigenvalues. B-type, okay? Now the crank's on the B-axis, so the eigenvectors are two. One eigenvector is bilaterally balanced against the x and the y axes, 45-degree polarization. The perpendicular to that, minus 45, or else 135-degree polarization, is on the other side. Those are the two eigenvectors to that crank. Those motions and those motions right there are your eigenstates. Anything else is a combination of those two, and it will undergo beats at the difference frequency. This difference frequency here. Whatever that crank rate is, omega b, one half is here and the other half is here. That's the total, what engineers would call a beat frequency. My druthers is to call this the quantum beat frequency, because we have a beat envelope which has to go two of the engineer periods to get back home again. And we saw that now it becomes circular polarization. If you start with the A type, it is as far away from being an eigenstate as you can be for B-type crank vector, which would be going this way. Now I've put it that way because most of the times the Hamiltonians that we describe have B equal to minus quantity. We'll talk about that later on, but you can see it has to be for a spring matrix, you see. This has to be a minus if you have these things set up with a coupling which always resists any positive motion that you make with either one of these. Okay? Or it gives you a positive force if you have a negative motion. That's Hooke's law, minus k times the distance. So I always put the crank over on this side for a mechanical device. Well, it turns out you have to do that for the quantum mechanical ones as well, because waves are spring-like, as you'll see. Finally, Mr. C, the weirdy, curly, chiral, cyclotron, Coriolis. Go on for minutes, I guess, with things that begin with C that are described by that crank there. And we've already seen that. That's the Foucault pendulum, oscillating this way, then oscillating this way, then oscillating this way, and so on. Passes the 45-degree mark, and again, it's as far from either of the other two as you can be, and comes down, and finally, a half wave plate, quarter wave plate gets you here, a half wave gets you here, okay, and then you keep on going, and you come back, well, out of phase. That happens with all of these, okay? So that's the eigenstates. The eigenstates consist of either right circular polarization right there, or left circular polarization right on the other side there. And I'm not pointing at that red thing, I'm pointing at a green thing underneath it that's coming out of the back, or would be coming out if I drew it. Okay? So again, it's the same deal. Half of a C frequency times 2 is the total B frequency for this focal motion. Now, the weird ones, okay? Where we have a combination. I've got a little bit of A and a little bit of B, okay? Some amount of this, some amount of this, no C, okay? So that puts me somewhere on the line between A and B as far as my crank vector goes, okay? I've got the crank vector pointed down, so this is rotation that will be in this direction, you see. You put your thumb on the omega, and then that's the direction it's going to go. But it's going to go immediately out into the elliptical region here, and then come and be back to being a plane motion again, and then going into the board here, and finally return up at the top. Okay? So it's a little bit more complicated than what we've talked about before. So we're going to have a certain amount of the B type and a certain amount of the A type right here, and this angle is going to determine how much. That's one way, at least, to describe this. Now, we already worked out a formula for this, and this is the result of the eigenvalues. If I had no omega 0 at all, I'm just taking a situation where I have A and minus A, no D at all, okay, and the B. All right, so this is a very thing. It doesn't have any overall frequency at all. It only has a difference frequency. So this is one where the eigenvalues are going to be centered. I'm going to have a positive eigenvalue, I'm going to have a negative eigenvalue. That's it. I have 0, something to goof up the perfect antisymmetry here. But what I'm thinking of now as a physical problem is this fellow here. If I've got a molecule here that matches what we're talking about, I did have it here. Here he is. Ammonia consists of hydrogens with a nitrogen. Nitrogen is not its right color. I think blue would be its color, sky, right? But if you're in Pittsburgh or in the 50s or Los Angeles, you can have a different colored atmosphere, like black. If you're in Houston, right, when one of their refineries is burning, that's the color of the atmosphere. Out where we are, we've got a blue nitrogen there, so I'm sorry about that. But anyway, the idea is that there are two states here. One state is where the nitrogen is sort of stuck on the bottom of the hydrogen triangle, and the other state is, well, you could say it would just rotate, but this is different. We're not going to have any of those degrees of freedom available. We're only going to have the degree of freedom of going through, turning inside out like an umbrella in a windstorm, so that it looks like that. Okay? So these two are tunneling states. And it's completely a symmetric thing. We know what the eigenvectors look like for this. They consist of this plus this. That happens to be the ground state, the symmetric combination. That's this one right here. And then an anti-symmetric combination. I'm trying to sketch the wave functions of the nitrogen relative to the hydrogens, imagining they're fixed, which is a bit of a stretch because they're much lighter than the 14 weight of this atom here, the nucleus of that atom there. But in any case, I'm drawing a wave function relative to them that's, sort of a blob, and then a blob with a node. This is opposite phase, so I have to have a node in here. It's like a p orbital if it was an electron. This is more like an s or a sigma orbital if it was an electron. So that's what we're dealing with here. We're dealing with a symmetric combination in the ground state. and an anti-symmetric combination in the excited state. That means that this B here has to be minus. That's why I drew the crank the way it was, and that's why I'm putting this one here. This is an amazing thing about quantum mechanical waves, is that if you twist a wave and put a kink in it, a node, you pay with energy, always, no matter what the potential is given the symmetry here. This is something that Schrodinger proved early on. It's a not well publicized fact that we'll talk more about it as we get into the finite groups. But this is a representation here of the x and the y, if you want to call this one x and that one y, eigenstate that is symmetric 45 degrees relative to being wholly in the down state and then wholly in the up state for nitrogen position. You see, this is half and half. That's what this means. Half and half with positive sign. The eigenvector of this matrix we all know and love at this point, 1, 1 over the square root of 2. This is a bra being drawn here, so I put a plus sign in that. Okay? Now, what we're going to do is we're going to mess up the symmetry. And the way we're going to mess up the symmetry of this is we're going to apply an electric field that can effectively pull on the nitrogen, because there is a charge imbalance. So one of the nitrogen is so lightly positive. I'm kind of making that up, is the way I think. But anyway, it's got a different sign than these guys, a little bit of charge imbalance, so that when I apply an electric field to it, it tends to drive the nitrogen in this direction if I put the field there. If I put the field this way, it tends to drive it further away from the tunneling point. And the same thing with this one. If I put the field, and it just stays there, but it will be very happy to move. If I put a field down, it will want to encourage it to go that. So I'm going to be adding some of this A stuff. So this is the A axis here, okay? As I change the A equal the dipole moment of the charge distribution times the electric field to positive, you see, I'm going to be encouraging the behavior that would drive this thing this way, so that it would be tending to, I'm sorry, it's actually the other way around, I think. No, that is that way. This is the ground state, and that's the way it would go in the ground state. You see, if I put an electric field on this thing, it tends to want to go down the hyperbola. This is the hyperbola, this is the eigenvalue. This is A squared, which is PE, quantity squared, plus the tunneling thing. The tunneling thing is just that distance right there. There's minus B, there's plus B for the eigenvalues for this and this. But what if I've got an electric field? Well, that's going to move our little spin vector over. It's going to make it so that we have combination states that have more and more of their distribution in the direction of the field. And what's really cool is that if you're in an excited state, just the opposite happens. When I have a positive E like I do here, the excited state is contrary. The ground state is obedient. The field goes this way, it goes this way. Field goes this way, it goes this way. Okay? It's like the ordinary citizen is obedient, right? The excited state, the rebel, right? Field goes that way. Ah, fuck you, I'm going this way. And then we're just talking about eigenstates, okay? Now what happens if you wiggle it and move it? We're going to be talking about that later on. But this is just if you gradually turn on a field, your ground state's going to get more and more over like this and get lower and lower in energy. Until finally, if you really have a big field on there, if you really have a big difference between this and this, who cares about that anymore? The little tunneling is going to be very much less in effect as I approach the asymptote down here. Very much less. You see, very quickly zeroes in on a plain old elementary dipole displacement, Hooke's law. This is assuming that the thing will stay together in an electric field of that magnitude.
So, can't we say that it is unstable and stable equilibrium?
See that last part.
Can't we say that it is unstable and stable equilibrium?
Oh, good question, because that is really the point of Towns's experiment, was to get them into an excited state so they wanted to go for the big field. You see, they get sucked in. And that's the ones he wants, because then he can put them in a maser and pump them out. Pump their energy out.
Cool.
That was the trick. Good question. This one is the one he wanted. These guys, when they see a big field, oh, nice big field, I'm heading out of here. Whereas these guys say, hey, I'm going to go. I'm going for that big field. Those excited ones. Yeah. So this is very right to use that energy as a potential for the whole molecule. And that's the way he could funnel them over to the maser. Yeah, that's very much good. Now you can see the motion of this one right here in the diagram of up versus down is very 45. As I go over here, it keeps getting more and more favored in the y. As I go over here, it gets more and more favored in the x, you see. If I call this one x and that one y. Call this one x and that one y. Okay. This little xy plot of the oscillator, right? This two-dimensional oscillator, okay, is more. And again, as I go over here, it's more and more. It says, hey, give me more field. I'm going to get bigger and bigger on this side. Bigger and bigger on this side, until finally there's nothing left on the other side. I've literally pulled the nitrogen either to this side or to that side, so that now it becomes more classical. This becomes a classical eigenstate. Whereas when you have it perfectly balanced, it has to treat both of them equally, and so it ends up with amplitude equally on both sides. And it does it in the excited state too. Except now when you apply the field, it's contrary. It's being contrary. And that's raising the energy. So that's a pretty big physics problem is being developed here in 1950s. Okay. Now I want to show you something, and maybe we zero in on this so that my tiny writing is at least partially available. I want you to see the difference between writing the Hamiltonian in the A basis and maybe transforming that using that transformation that we derived with a double oscillator that was equal to its inverse. This was the thing that transformed you from the local mode to the symmetric antisymmetric mode, symmetric antisymmetric, symmetric antisymmetric mode. Okay? So if I apply this similarity transformation to my A basis, my view of this Hamiltonian in the up-down basis, okay, and use the eigenbasis of this of just the B part to be a new home, so to speak. Okay, taking the square roots out and putting a half here, so I can multiply these two matrices. Either way, these are associative things. That's one of the rules of group theory, is that you can associate those matrix operators, and you end up with this, which I think is really cool. Let's finish it. Get that 1/2 and the 2 out of there. You literally replace A with B. Now B's on the diagonal. Well, that's where it's supposed to be, right? This is an eigentransformation for B, but it's an anti-eigen for A. Everyone should know about this. This is the simplest example of basis change that really, yeah, I can get with that. I can see what happened. So if I'm in this neighborhood, I want to be in this basis and let this be the perturbation. You know, the A is going to, I'm right here as an eigenstate with equal. Now I go this, just a little bit over, well, this thing is going to do something to me, you see. And that perturbation will, as you know, cause these to split apart.
Sorry, are those transformation matrix are unitary?
You bet. They're even better than unitary since they're orthogonal. But they're even better than that because they're orthogonal Hermitian. And that was a trick. Yeah, I could have put the minus up here and then I would have had to put it down there, right? Here they're equal. So it's really a special transformation. You don't get this kind of stuff very often. This kind of supersymmetry. Okay, but yes, you're right. So this is a Hermitian operator because it's a Hamiltonian always. The transformation that diagonalizes it is going to be unitary, but if it were real numbers, it would be orthogonal. Okay, but it usually isn't going to be equal to its inverse, right? And that's a situation we have lucked out here to have. Okay, now I mentioned the perturbation because if that's the sort of thing you have, the way you do perturbation theory right off the bat is simply say your new eigenvalue is going to be E1 plus the square of the off-diagonal element, and I mean absolute square because this might be complex and then they'd be conjugates, divided by the difference in energy. In this case, E1 minus 2, whatever energy you're talking about is first. And then down here, energy 2 is first. Okay, so one goes up, the other goes down because one of those is positive, the other is negative. So that takes care of the beginning of the hyperbola, sort of a second order perturbation that we're doing is a parabola. Okay? And that sticks with a hyperbola for a while. Okay? But here's a very important message. You see, here's the exact result, okay, which is a hyperbola, not some polynomial that you're going to get by doing a perturbation theory, say to 10th order. If you do a perturbation theory to 10th order, you get something that comes out. I don't think I even bothered to draw the 10th, but if you go up to 8th, you get this thing, you see. And if you go to a 4th, you get this. If you go to 6th, you get to this. What you can see is the 4th order perturbation, which is the next in line. They're all even. Okay, the 4th order perturbation, you see, only goes a little bit further than the second order one does, and then it peels off. You see, the second one peels off about here. The 4th one peels off about there. Then the 6th peels off about there. And that's the way it's going to go. You're just going to be creeping. You go to the 100th order, you'll be here maybe if you're really lucky. This is why quantum electrodynamics and field theory, the way we do it, the real pain. Perturbation theory just simply doesn't work. If you're trying to get things in terms of polynomials, you're never going to make the hyperbolas and the sine curves and the things like that nature uses. And I should point out to you that this avoided crossing here is the same kind of avoided crossing that we have, and we might as well swing the camera over to this little picture here. The avoided crossing of positive mass and energy states in frequency versus wave vector. That's the so-called mass shell right there. And there's another one just like it below the blackboard tray here. It's symmetrically displaced, exactly like the hyperbola that we just did for the ammonia energy levels. So my challenge to you is make a connection of this with what we're talking about in the two-level world that we were just looking at here. So this is direct quantum mechanics in its very simplest form when we're talking about frequency versus wave vector or vector potential. Either one or both at once. Okay, so here's a picture of the whole cone associated with the electric field this way, the tunneling into the board, okay? That's the B axis right there, this is the A axis right here, and there's the avoided crossing that wasn't avoided. And of course, that is a miracle point, and we're so lucky to have a compound, shall we say, two-dimensional lattice, graphene, that has electronic structure that produces very good approximations to a conical intersection. And we'll talk a little bit about that and other models that have things like that later on. Now, at this point, we're getting fairly close to the end of what we can do. I would say that at this point, I'm going to let you go ahead and read, if you're interested in the optical polarization business, because you see the Euler angle alpha here is equal to, and here's the factor of 2 coming out, because this is Stokes vector space, so everything down here gets doubled up here. But this phi here is now, I'm using it as an alpha over 2. It's the actual tipping of an ellipse that is called, I guess you would call that Faraday rotation, but it's like the, if it were actually going to be occurring in time, we would call it the Foucault precession of an orbit. And it doesn't matter what size that orbit is, but the size of the orbit, as the aspect ratio, is determined by this little angle here, and that's an Euler angle beta. Beta is equal to 2 times that angle up here. Here, the actual angle is 1/2 of the Euler angle in the Stokes vector space. This is spinor space now, you see, X versus Y polarization. So I point that out because that's one very nice representation of our Euler angle descriptions. And then there's the Stokes vector, the spin vector right there. You change your normalization. Here it's the square root of the intensity, that's the radius up here. This is the intensity, which square rooted. And this is why I say this space is the square root of that space that we live in up there with the A, B, and C, or X, Y, and I'm sorry, X, Y, and Z is the stuff that we've been talking about. And also I like to show you the dynamics of an oscillator. We've already seen this birefringence for A rotation. That's where you had no coupling, but you got this thing that became, that went from, say,